Yes, so in this session, let us start with the discussion of our ripple carry adder and carry lookup our BCD adder. Let us try to discuss them. So in gate level modeling, we'll discuss them. First of all, let us see the block diagram of that particular designs and let us move forward. Good evening. I think you are facing some tool issue, right? So let us start this. Now, uh, let us start with the design of our ripple carry adder, 4-bit ripple carry adder. Let us try to design using gate level modeling. So for the 4-bit ripple carry adder design using gate level modeling, this is the block diagram which we are going to follow. So we are going to have four full adders like this. This is full adder 1, full adder 2, full adder 3, and full adder 4. Okay, 4 full adders I'm going to have. And I'm going to have my inputs A0 and B0, A1 and B1, and A2 and B2, and followed by A3 and B3 are my inputs. Okay, and I'm going to have my S0, and the C0 is given to this my FA2. This is, let's say, S1 and this is C1. Okay, here I'm going to get S2 and the C2 is going to given to this FA3, and S3 and C3 is given to FA4 and S4, and this is my C4. So this I need to design using gate level model. So let us see how to design this ripple carry adder. So for designing our ripple carry adder, we need to first of all have a design of full adder. Okay, let me show you. So let me create a module which is known as ripple carry adder. Add sources, create file, ripple carry adder is my file name, followed by OK and finish. So I've created a file which is known as ripple carry adder, and after that you can open that file by double click on that. Open that file, and in this file let us try to design it. So our ripple carry adder have inputs. Let me zoom in. So the ripple carry adder inputs, let us name it as RCA, A underscore RCA, B underscore RCA, like that. A underscore RCA. Now here I can declare these inputs one by one, like let's say suppose input A1 underscore RCA, comma B1 underscore RCA, comma A2 underscore RCA. Like this I can include all the inputs, or else I can use the concept of vector. Okay, so I'm going to use a concept of vector here, 3 down to 0 A underscore RCA, okay, comma 3 down to 0 B underscore RCA. So I'm going to use a vector for declaring this A underscore RCA and B underscore RCA, and input Cn. Okay, and output is also 4-bit, 3 down to 0 sum underscore RCA, and I also have output Cout underscore RCA is my input and output ports for my ripple carry adder. Okay, now I'm going to instantiate my full adders inside my design. So already I have written the code for my full adder. I think no, I haven't written. Yeah, I have already. Yes, I have the code of full adder already written. Okay, so what I'm going to do is I'm going to write it down here. So the full adder which I have written, the name of this is FA. Let me write it down again. Okay, I have already written FA. Let me write it down. Let me instantiate here FA. And so for the first full adder one, let me give the instance name as FA1. Okay. For the first full adder, I need to provide A, B, and C in, and I'm going to collect my sum and carry. So here in this particular design, we can see we need 1, 2, 3 wires. Okay, let me declare them. Wire W1, W2, and W3 are my 3 wires which I'm going to declare, and I'm going to connect my A of 0 with my first full adder input. So how I'm going to connect A underscore RCA of 0. I'm following connection by order. Okay, and I'm going to pass B underscore RCA of 0, and Cin is connected to the first full adder. You can see the diagram. So Cin, I haven't written it. So Cin is connected over here, and followed by I'm going to collect my sum. So sum is directly connected. So I'm going to collect it into the variable sum underscore RCA of 0. Sum underscore RCA of 0. Okay. And Cout is connected with a wire. So this is how I'm going to connect my first full adder. Okay. And let me check whether the order is correct or not inside my full adder. A, B, C, output sum and carry. Yes. Okay. Now let me instantiate the second full adder FA, FA2, A underscore RCA of 1, B underscore RCA of 1, the first output of full adder, that is carry, is being given to the second full adder, that is W1, and sum underscore RCA of 1 and W2. Now full adder 3 FA3, A underscore RCA of 2, comma B underscore RCA of 2, comma W2, comma sum underscore RCA of 2, comma W3. Okay. And followed by last full adder instance FA4, A underscore RCA of 3, B underscore RCA of 3, W3, sum underscore RCA of 3, and here I am going to collect it Cout underscore RCA. Okay, and followed by end module. So this is my simple ripple carry adder code. So I'm going to instantiate all my full adders. So is it clear for everyone? Any doubts or any queries in this? So before going to elaborate it, let make sure that you are setting it as stop and press on run elaborated design. Let me press open elaborated design. And 1 minute, I think I have a syntax error. Let me check where is the syntax error. Okay, already end module is present, right? So remove it and save it and click on open elaborated design and press OK. Yes. So is it clear for everyone? Any doubts or any queries in the ripple carry adder development? Okay. Meanwhile, we will see the BCD adder design, and let us, according to the design, let us try to write down the code for our BCD adder. So your BCD adder we have discussed in the digital design also. Let us discuss it one more time. So this is our BCD adder where we are going to have our 4-bit binary adder, 4-bit adder, two 4-bit adders we are going to have, 4-bit adder. Okay, and we will get our S3, S2, S1 and S0. These are being connected to this, and here we are going to give B3, B2, B1 and B0, and A3, A2, A1 and A0. Okay, and we also have one logic. So this connected with our S3 and S2, and this is connected with our S3 and S1, S3 and S1. Okay, and this is being connected to the this pin, and this is 0 and this is 0. This is B3, B2, B1, B0, and this is A3, A2, A1 and A0. This design we have already seen in our digital design. This is our output carry. Yes. So, and here the carry which we are getting, we are going to ignore it. We are not going to consider it. We are going to just simply ignore it, and we are going to get S3, S2, S1 and S0. This is the actual sum we need. Okay. Yes. So this particular design, let us try to develop the Verilog code using gate level modeling. Okay. Yes. Already shared that particular link in Telegram, like how to install the Vivado. You can once refer. Vivado will support the code coverage and functional coverage. Functional coverage and code coverage, I don't think Vivado will cover. We need QuestaSim for that. Yes, so this is the ripple carry adder design which we were discussing previously. So this is a design which is being synthesized, elaborated design. So this is our full adder. We have 4 full adders which are being connected, and this is our design of our ripple carry adder. Okay. Now let us try to design our BCD adder by referring the by referring the diagram. So let me create one more file. Create file BCD adder. So I will open this file BCD adder 2, and let me write down the input and output port list of this. We have inputs of the BCD adder are 4-bit inputs, 3 down to 0, A underscore BCD, and 3 down to 0, B underscore BCD are our inputs, and input C in are our inputs, and we have outputs as 3 down to 0 sum underscore BCD and output C out. Okay, so these are the inputs and outputs of our BCD adder. Okay, now we need how many wires? So we need 1, 2, 3, 4 wires, and 5, 6 wires we need. Okay, so let me declare those wires. Wire W1, W2, W3, W4, W5, W6. So total I am going to have 6 wires which I am going to declare, and for this adder I am going to take a ripple carry adder instance which I have created previously. Yes, so I am going to take the ripple carry adder design which I have taken. Where is my ripple carry adder? This is my ripple carry adder design which I have taken. So ripple underscore carry underscore adder is my design name which I'm going to take, and I'm going to instantiate over here. So ripple underscore carry underscore adder RCA1. Okay, and I'm going to connect my A here, A underscore BCD, to this ripple carry adder. Okay, so we can see the diagram here. A3, A2, A1, A0 is connected to here, and B3, B2, B1, B0 is connected over here. And ripple carry adder also, we have 4-bit input A and 4-bit input B, which I'm going to connect A underscore BCD, and B underscore BCD I'm connecting it, and followed by C in. And the output which I'm going to get is to be collected inside my wires. So what I'm going to do is I'm going to take a wire sum underscore temp. Okay, that I'm going to use it here, sum underscore temp. So the sum which I'm getting from the ripple carry adder, I'm storing it in the wire, and the carry also I should collect it, right? So wire cout underscore temp. Okay, so I'm going to collect over here cout underscore temp. Okay, now so we can see from the diagram we have 2 AND gates and 1 OR gate. I will write down here. So AND A1 and OR O2. Okay, and we also have one more ripple carry adder. Let me copy this and paste it over here. So this is one more ripple carry adder which we had having now, and we have 2 AND gates and A2. Okay, now this AND gate is fed with S3 and S2, and the output of this AND gate is, let's say, another wire. Let me declare one more wire here, wire A1 comma A2 comma O1. Okay, yeah, so my output of AND gate is A1, and the inputs are S3 and S2. So where is S3 stored? S3 stored inside sum underscore temp. Okay, so I'm going to write sum underscore temp of 3 comma sum underscore temp of 2. Is it clear up to here? Any doubts or any queries? So basically I'm getting this sum, right? S3, S2, S1, S0. Okay, that I am collecting it into a wire. Okay, so what I'm doing is I have created a wire which is known as sum underscore temp of 3 down to 0. And when I'm instantiating my ripple carry adder, I'm connecting my input A and I'm connecting my input B, and also I'm connecting my input C in. Okay, and the output sum which I'm getting from the ripple carry adder, I'm collecting inside my sum underscore temp variable. Okay, and the carry out which I'm getting from a ripple carry adder, I'm collecting inside another wire which is known as C out underscore temp. Is it clear how I am collecting my sum from the ripple carry adder one and carry from the ripple carry adder one? Exactly. Okay. Now afterwards, what I'm doing is, from the diagram you can see the sum. In the sum, the MSB is connected to the AND gate input and H2 is connected to the AND gate input. So that is what I'm writing here. So AND gate output is a wire A1 and sum underscore temp, that is third bit, is connected to input of AND gate and second bit is connected to the input of AND gate. That is what I've written here. And already A1 is created, so we cannot use A1. So we will use A underscore 1 and A underscore 2. Okay, and O underscore 1. Here I am going to use A underscore 1 is my output of our AND gate. Okay, and coming to second AND gate. Coming to second AND gate, S3 is connected and S1 is connected. So how I can write it? S output of my AND gate 2 is A underscore 2 and input of my AND gates is sum underscore temp of 3 comma S3 and S1 are connected at sum underscore temp of 1. So this is how I'm making my connections. Okay, yeah. Now coming to OR gate. OR gate, we have inputs as wires and output is one more wire. Okay, so output of my OR gate, let us say it is O underscore 1. Output of my OR gate is O underscore 1 and input of my OR gates is A underscore 1 and A underscore 2. That is my output of my AND gate. You can see the diagram also. Output of my AND gate is connected to input of my OR gate. That is what I am going to do. Okay. So what I am going to do is I am going to write A underscore 1 comma A underscore. So now what I am going to do is I am going to write it down. I have one more ripple carry adder. So I have two adders. Okay. So I need to make these connections. Okay. Second ripple carry adder connection. Now you can see, let me erase all these connections in the second ripple carry adder, and you can see the inputs of this A3, A2, A1, A0 are directly connected to S3, S2, S1, S0. That is sum. So what I'm going to do is here sum underscore temp. A is connected directly to sum underscore temp. That is this wire it is connected. Okay. Now what is B connected to? B is connected to only this B3 and B2 and B1 are connected to the output of OR gate and remaining two inputs are equal to 0. Can you able to see this? Only B3 and B2 are connected to output of OR gate and B3 and B0 are equal to zeros. Yes or no? B3 and B0 are connected to 0 and B2 and B1 are connected to OR gate output from the diagram. This we need to write down the code. A3, A2, A1 are connected directly to the wires. Okay, that is sum underscore temp. But I need to connect my only B2 and B1 to output of this OR gate and B3 and B0 to 0. Now, how to do that? Now, how to do that? So, how to make that connection? So, I cannot write B B2 comma B1. Okay, I cannot write like this. Okay, why I cannot write like this? Because inside your ripple carry adder code, let me show you the ripple carry adder code. So where is your ripple carry adder? So inside your ripple carry adder code you have only few arguments, that is 1, 2 and 3 arguments, that's it. Okay, but how many arguments you are providing here? 1, 2, 3 and so on. You are going to give b of 0. Okay, like this you are going to give. No, you cannot do like that. So for this what I am going to do is I need to write it down like this. Assign b of 1 minute. Let me zoom in. So what I need to do is I am going to take one more wire actually. So I'm going to take wire 3 down to 0 B underscore RCA underscore 2. Okay. This B underscore RCA underscore 2 I'm going to provide it to my ripple carry adder 2. Okay. This is my ripple carry adder 2. Okay. Now So I'm going to use a keyword which is known as assign. This keyword I've explained you previously also. For assigning the values to the wire, you are going to use it. Okay. B underscore RCA underscore 2 of 0. So what should be the 0th pin connected to? So you can refer the diagram. So the 0th pin of your B naught should be connected to 0. So you are going to write which is equal to 0. Okay. And your third pin also should be connected to 0. Right. Assign B underscore RCA underscore 2 of 3 is equal to 0. Okay. And the remaining pins should be connected to the output of your OR gate. How to connect that? Assign B underscore RCA underscore 2 of 1 is equal to O underscore 1, and assign B underscore RCA underscore 2 of 2 is equal to B underscore RCA underscore 2 of 2 is equal to O underscore 1. And after that, what I'm going to do is I'm going to copy this and paste it over here. That's it. So what is happening? This B underscore RC underscore 2 is a wire where 0th pin is connected to 0. Second pin is connected to O underscore 1, that is output of OR gate. And first index is also connected to OR gate output. And 0 and 3 pins are connected to 0. That is this particular connection I'm making. This is 0 and this is 0 and these two pins are connected to my OR gate. Is this clear for everyone? Yes or no? Please let me know in the chat box. Okay. So this is how I should make my connection. This is how I should make my connection. Okay. Now I have one more. Thing which is nothing but Cn of this ripple carry adder that I am going to provide at 0 because we are not going to consider that comma 0. Okay. Now I should collect my outputs. So first one is sum. Sum is directly connected to sum underscore BCD. Okay, the sum is directly connected to the output, that is sum underscore BCD. I will write down here sum underscore BCD. And coming to carry, carry is discarded. Anyways, I'm going to write down C out. Okay, that's it. So this is my BCD added design. Okay, let me save this and let me make it as a, and let me click on schematic. Let me press on reload. So the reloaded design will be given. So the code, is it clear for everyone? Anyone having any doubts in the BCD adder? You can once try it on your own by referring this. You will get a clear understanding. Okay. Yes. So this is our design which we are getting. So this is RCA1 and this is RCA2. Okay. And we have our AND gates and whatever the connections which we have. So this is our S0 BCD, S1 BCD and S2 BCD, S3 BCD and C out underscore BCD. Okay. And this is our RCA design. Okay. And by now you might understood one thing, that by just seeing the schematic diagram, we cannot able to judge the functionality of the design, whether the design is working correctly or not. Okay. We need a test bench for verifying that particular design, whether this design is working correctly or not, whether the functionality is correct or not. By just seeing the schematic, you cannot judge. Okay. By referring to this, by developing the test bench only, we can able to verify that. Okay. So after learning the test bench of how to write the test benches, everything, we will come back to this particular designs and we will write down the test bench for each and every design and we will verify. Okay. That is the motto. For now, we are just following the schematic diagram and we are going to write down the gate level modeling code. We don't know whether the functionality is correct or not. We need test benches for that. Okay. Yes. So that's about this particular ripple carry adder and carry look adder. Yes. So that's about this particular session. If you have any doubts or any queries, you can stay and discuss with me, or else you can leave the session. Okay. Thank you.